All right, so my name is Chandler Carruth. I'm up here to talk to you about high-performance code. How many folks are here at CppCon for their very first time? Woo! Oh my goodness, that's a lot of people. Okay, so how many folks have seen the talk from 2 years ago on YouTube? Okay, that's better, because I'm not going to repeat that talk. So this is kind of the second of a series, right? The idea is that the first time I talked a lot about kind of things that really limit high-performance code, kind of patterns you want to develop, fundamental things you want to do over and over again. But I felt bad about that talk for one reason. One reason was that it was very negative, right? Like, it wasn't actually a very constructive talk. I didn't tell you guys a lot of things you can do and you should do, or kind of new and exciting tools to try and help you out writing really fast code. So this talk is going to try and be a little bit more upbeat. It's going to try and help you guys out a little bit more. We're going to try and actually go through and describe some hybrid data structures that are going to hopefully be very useful for you when writing really fast code. Just as a little bit of background, if folks don't know, I work at Google. I work on the LLVM compiler. And in particular, I'm actually going to be talking today about LLVM's internal data structures. It turns out that LLVM is a great example of kind of like really high-performance code, because you have a bunch of compiler nerds, and I mean a bunch of really kind of bad level of compiler nerds, all of them performance nuts. I might be a good example of this. And they're all working on this compiler, and we actually care a lot that the compiler itself is very fast, right? And you know, we're all thinking about kind of modern computer architectures and the challenges that we face when we try and make compilers run really fast. And so we end up writing a bunch of great data structures, writing a bunch of algorithms, and spending a lot of time really tuning, examining things to try and get the absolute best performance out of this. So I actually think this is a great place to kind of figure out about high-performance data structures. So this talk is I'm going to give away all of the secrets of this talk before we even get into it, just so you know. There's nothing up my sleeve here. All right, so vector sets and maps. That's it. That's all we're going to talk about, whole hour, but it's going to be awesome, okay? So the very first data structure is, of course, a vector. Okay, so this is what LLVM's vector kind of looks like. Now, I could have shown you the real code from LLVM, but if I had, like, you would all have to be standing up here in front of the screen and squinting really hard, and it would be really confusing. So I've kind of distilled all of this down to the bare essentials to kind of communicate the essence of how LLVM is making these data structures fast. So this is a pretty straightforward, small-sized optimized vector. That's the key idea. It's a small-sized optimized vector. Now, that doesn't mean that we expect all of the vectors in the entire compiler to be small. That's actually not the point. The point is to save on the early small allocations, because it turns out those end up being a really large component of the cost of vectors. And by doing a small-size optimization, we don't have to allocate those on the free store. We can very quickly use an internal buffer for those, and we only actually reach out to the heap for allocations when we're growing to some substantial size. This is easily the most fundamental data structure that we use in the entire compiler. When I get up and I talk about how, no, vector's all you need, like, really, I live and breathe that advice, okay? We use this thing for queues, for work lists, for stacks, every single kind of basic operation you would imagine, everything down to and including binary heaps and priority queues. All of them are built on top of the back of a small vector in LLVM. Now, I get a lot of kind of immediate responses of, why on earth don't you just use std_vector? You said that data structure at least wasn't completely broken in the standard. I'm sorry, it is. So even std_vector has a really bad problem in the standard, because in the standard we specified that the iterators are not invalidated if you move the vector from one location to another. Now, this can be convenient at times, but it has a real problem. If you can't invalidate the iterators when you move from one location to another, you can't do a small size optimization. You can't do it at all. It's completely off the table. I think this is terrible, right? Small size optimizations are a huge win. They're a huge enough win that the standard even uses them in the other vector in the standard that's spelled in a very awkward way of std basic string. I don't encourage you to write, a custom char traits specialization just so that you can use std basic string for your vector. Instead, I think we actually need to have a small vector, and that's what LLVM uses. But we can do more interesting things than just small size optimizations. So LLVM's vector has this kind of weird trick that it uses. So we kind of take, on the left-hand side, a lot of the guts of the small vector out, okay? And we just leave that small size optimized buffer, okay? Then on the right-hand side, we have a base class. And this base class is interesting because it looks exactly like a vector. Nothing fancy here. This is just a vector. It has all of the operations that you would expect to have on a vector. It just doesn't have the buffer. And we pass the buffer in dynamically through the constructor, right? This is actually a really simple pattern. But this is powerful because now in our interface boundaries, whenever we want to have an output parameter or an input and output parameter that's a small vector, we can actually type erase the size. We can remove the size from the type completely, and we don't pay any overhead, we don't pay any abstraction boundaries, right? We don't have any cost to it. We actually just have this nice slicing right across the type boundary. This is really, really powerful. So all of our interfaces end up carrying small vectors without baking in a particular size. This even lets us do crazy things like have different callers to the same routine select different small buffer sizes based on their use case, based on their expected workload, which again is a really powerful way to have hybrid data structures that adapt, that fit the problem you actually have, rather than being, baked in stone in one particular design. Okay, so that was vector. Now we have to talk about sets, okay? So the set is actually the same thing, all right? This is a really unoriginal talk, I'm sorry for that. So the set is also just a small size optimized set. But we aren't doing the set the same way that stood unordered set works, for example, okay? We're instead using open addressing here. We just have an array of buckets, flat in memory. We use quadratic probing. I didn't want to write quadratic probing up here on the slide because it's really boring and it's really gross, right? But it's a very straightforward approach, right? You just probe a flat array of buckets, nothing to it. And when you have a small size optimization, you can even save on the allocation. You have an inline buffer that you get to start off your bucket array with, okay? Really, really straightforward thing. Now the last thing you're gonna see on this bottom is that we have a traits object. We actually put all of our hash table traits into a single traits object instead of having two, the way unordered map does and unordered set does. And it has, the kind of expected things. You can get a hash, right? You can actually hash the value. You can also compare things because we want to have the ability to compare things in a customized way. But we also have two other routines. You can get an empty value and you can get a tombstone value. And this is actually what allows a very simple approach to a flat quadratically probed hash table to work. We need to be able to create this bucket array, right, and populate it with empty keys. And we need to know that they're empty so that we know we can put new entries into them. And if we start probing and then start erasing, we need to leave markers behind so we understand that there actually are values along a probing path, right? And you have to keep probing. It's not just an empty slot. And we use tombstones for that. This does require your types to expose two kind of, fake values that you can identify. It's really important, but most of our types we can do this with. That's it. This is all of the logic that goes into us having a set. And you can imagine then what the map looks like. The map just generalizes this to a key and a value, right? We still use the same traits, right? But it's focused on the key. We actually have to re-implement some things because we want to be fairly careful about the value here. One thing that LLVM tries very hard to do is that for empty buckets and for tombstone buckets, we don't put a complete pair into those buckets. We actually just put the key into them so that the value in the pair doesn't actually have to have these special states in it. And that requires some special code. It's not too fancy. And of course, we layer a small size optimization on top of all of this. All right? So that's the talk. 10 minutes, what do you think? Right? Okay. So there are a few other things we should probably discuss before we call it quits on this though, okay? But this, I do want to emphasize, that is the core foundations of all of the data structures that we use throughout the entirety of LLVM's compiler, okay? Almost everything else you see that's really interesting is a very domain-specific data structure. It's one that we've crafted to solve a particular problem with a very particular set of constraints. other data structures you see tend to be abstractions around domain-specific problems. They don't tend to be fully general. They tend to have really particular use cases. The general purpose tools we use, like 99% of the time, are just these 3 tools, okay? Also, if you're like looking in the LLVM code base live, by the way, they're all spelled differently, and like they suffer from over a decade of kind of organic growth. I've cleaned a lot of this up to try and just present the core ideas here in a way you can get. But we should at least talk about one thing before we get out of here. Some people get really grumpy about these small size optimized containers. And when I say some people, I mean at least one person in the audience, because they tell me over and over again, I should be using an allocator for this. I don't need to build yet another container. So I want to actually talk about this so we understand why LLVM continues to actually use custom containers rather than allocators. It's interesting, right? So allocators seem like they should work. So this is lifted directly from Howard Hennant's suggestion to the LLVM community that they should stop writing custom containers and use allocators. And he proposed this version of small vector, which relies on a short allocator that has a lot of code in it because allocators require a lot of boilerplate. It's actually really simple though. It just looks like it has a small buffer in it, and it allows you to use that small buffer for the allocations in the vector. And you construct things in this way, and it works great, okay? This solution absolutely works. But there are 2 limitations to it that really get in the way of LLVM's usage patterns. The first one comes when you start putting these on interface boundaries, all right? And this happens a lot. We end up with a lot of small vectors on interface boundaries because they end up being a vocabulary container for us. But I've got a bug in this code, and I've got a bug in the code because I didn't remember to update the size parameter, and I have to keep these things in sync across all the different callers. I've also lost the ability to have kind of a customized size for different callers without the function I'm calling knowing how to do that. Now, I don't know how to solve this with allocators today. I mean, Howard may know how to solve this. Someone else may come up with a way to solve this, but looking at it, it seems really annoying to actually get this to work, to get the kind of very low-cost interface design that we have with a custom container here. The second problem I have, I think, is more fundamental. So one thing that we actually do, again, very often, is we have small vectors in the return type. And this actually works really well for us because people are using auto now, right? Throughout LLVM's codebase, we use auto. And so we don't actually write the return types for these functions very often. We don't have a lot of the actual small sizes scattered about the codebase of LLVM, right? They just have auto. You can update the small size where we return it, no problem at all. It goes, every single call site picks that up. But if you do this with an allocator, right, we have a bug here. Right? We're returning a vector that's allocated memory potentially on the stack, okay? And so this can actually lead to subtle bugs. And again, maybe there's a way to embed the small size allocator inside of the vector object, but again, it seems really challenging to me. And having a custom container makes all of these problems go away. We get our value semantics back for this container. And it's fairly easy for us to, pin down the value semantics we want, even when it's in a small size optimized state. And that's important. That's really, really important to the usability of the API. Making sense? Okay. Silence. So I've talked a whole bunch about small size optimization, right? And that's really the only kind of critical thing here. But how do you actually get it to be effective, right? Small size optimization works way better when your values are really small, right? When you have very high density to the values. And so the bigger challenge in a lot of ways than coming up with a bunch of fancy data structures that use small size optimization, that optimize for small values, it's like, how do we actually make things small enough to benefit from this? So a bunch of LLVM's time is actually spent making its data, its values, especially the ones we put into the data structures, as small, as compact, and as efficient as possible. And I'm gonna try and show you some of the techniques for that because it turns out that's more important than having the containers. The containers are easy. Using the containers and using them effectively tends to take a lot of work. Okay. So the first key idea here is to give large objects address identity. So what do I mean by address identity? The first thing to think about is, does your object have some intrinsic identity, right? Is your object like fundamentally unique? If you have two objects, are they going to compare equal, right? It turns out for a lot of large objects, especially that we work with in the compiler and that I've worked with at Google, most of the large ones have identity. There's something unique about that object, okay? And that means that if we allocate it carefully, if we allocate it at a stable location, we can actually borrow its address to represent that identity, okay? So we can just use the address, the pointer, as a stand-in for the identity of the object. And all of a sudden, we've taken the object, which is quite large, and we've made it a pointer, which is very small. I mean, in the simplest, trivialist case, you have a little vector of unique pointers for a big object. This seems like such a trivial use case. This actually comes up all the time in real code, okay? We do this in tons of places in LLVM's code. And this gives us a few advantages, right? It gives us stable pointers to big object. If we need to create a set or something else out of this, we have stable addresses here. They're not going to move around. If big object is very expensive to move, right, resizing this vector is going to be a lot faster than if we put the big objects in place in the vector. Okay, this can actually make things faster directly. If the big object isn't movable at all, if it contains, for example, a mutex, right, then this can be essential because there's literally no other choice available to you. Now, a lot of people look at this and they're like, why don't you use a list? This is what list was built for. And you're not saving any indirections here, right? You've got a pointer already. Just use a list. So there are two problems with that one, though. The first problem with a list is that a list doesn't have a pointer, it has two pointers, right? And I don't want to pay for anything I don't have to. I want this to be as lean as it can be. Now, I could use forward list, okay? But forward list comes with a lot of constraints, all right? It's very hard to mutate forward list. But it is just one pointer, so it would be the equivalent space here. An interesting thing is that this will often be faster than forward list, and for a somewhat surprising reason. So imagine you're walking this container. If you're not iterating the container, you don't care about the difference between list and vector. But if you are iterating this container, you're going to see an interesting difference between forward list and a vector of unique pointers. Because as you're iterating, you're going to be looking at one object, and then in the next object, and then the next object, okay? And you're probably doing this on a fairly modern processor, okay, modern CPU. And that modern processor, it's going to try and speculate a lot of the operations you're doing ahead of time. And so it's going to be doing things out of order. One of the things that the processor is going to try very hard to do is to figure out what memory you're going to reference next, okay? That's really what it wants to know. Now, if you write a loop over a small vector of unique pointers, right, you're going to be able to make that very clear to the processor because you have a loop index that's just an offset into this array, essentially, as far as the processor is concerned. And each pointer in that array, you load memory from. And so each pointer in that array is memory that the processor needs to populate into its cache and actually make available. What happens when you iterate a forward list, though? For a forward list, the next memory you're going to access, you can't find without reading the current element, okay? So if you get a cache miss on the first element of your forward list, you also get a cache miss on finding the address of the next element, okay? And that's true the whole way down. And this kind of thing makes a big difference when you add it all up, when you do this all over the place in your code base. So you want to think about these kinds of trade-offs when you're looking at data structures at the high end of performance. But this isn't enough, okay? Even this still isn't enough in a lot of cases. We're paying a pointer's worth of overhead here. We may not want to do that. We may not want to keep this vector around. We may accidentally end up with a very large vector that's only about 60% full. That may be problematic for some reason. We have some other techniques that we use as well. But probably the biggest reason to not like this technique is that it doesn't give you any locality for these large objects, right? They're just allocated wherever your memory allocator sees fit. There's no locality at all. So LLVM uses this really horrible piece of code, which I've actually simplified and made less horrible, but it's still pretty bad. So this is its hacked up variant of allocators, which is a terrible API. I'm not endorsing the API here at all, but the idea of it is really useful. What this does is it allocates chunks of memory, okay? And it allocates a large chunk at a time, in this case a whole page at a time. And it keeps those pages around, and it just hands out regions of those pages to users. This is essentially the world's worst malloc implementation, right? I mean, seriously, most malloc implementations start something like this. The nice thing about this is it's local. So I can create one of these for my particular code path, and I can carefully allocate large objects on one of these and force them to have strong locality, okay? And I will waste a lot of memory because I'm going to allocate an entire page ahead of time. Unless I allocate a large number of these, this could be very wasteful, but I can adopt a very simplistic model if I know that I'm going to allocate a lot of these and I know that I care about the locality. I can kind of adopt this model eagerly. Whereas a malloc implementation has to make a lot of very hard trade-offs. The big simplification here is that there are no trade-offs to make. We're essentially letting you, the programmer, make the trade-offs instead. So this does slab allocation. Every time we run out of space, we get a new page of memory. We then carve it up. It's really fast. It's incredibly fast, okay? The amount of things that this saves that a malloc implementation has to do, even though they look essentially the same under the hood, is astonishing. And this lets us get stable addresses and reasonably high locality for large objects, okay? And once we have that, we're off to the races. We can put those addresses into data structures and containers, and we can use small size optimization and other very cache-friendly techniques on those containers. Making sense? Hopefully? Okay. Well, we will keep going. So sometimes even pointers are too large, right? Sometimes you just have too many pieces of data. You actually need to pack things more densely. When that's the case, just use an index, right? We just talked about having a vector of unique pointers. If you have a small vector of unique pointers, you can use a very small index into that, and you can save a lot of memory that way. There are a lot of ways to kind of force the size equation down and down and down until you actually have small enough pieces of data to work with. Okay, so the next big ticket item here is to aggressively pack bits together. And this is probably the most complicated thing that LLVM does to make its objects small. Well, the first realization when you're figuring out how to pack bits together is we just spent a bunch of time turning everything into a pointer, right? I mean, a whole bunch of effort turning everything into pointers. You know, gotten a few of them. But fortunately, our pointers are a bit different from the XKCD pointers. XKCD pointers have these really unfortunate last characters, A, C, and E here. I don't know why he used those. Our pointers look something a bit more like this. And as a consequence of looking a bit more like this, there's an opportunity. There are these 4 zeros in the pointer. I love these 4 zeros. They're essential, okay? These 4 zeros are like the most valuable 4 zeros in my entire program. LLVM does everything in the low bits of a pointer. So this is where we're going to get most of the wins for packing data into smaller and smaller sizes. All right, now you see what I'm talking about when I say I have a lot of code. All right, so let's actually step through what this is doing. The very first thing we need to do is we need to classify things that are pointer-like. What does it mean to be pointer-like? Well, it means that you can be converted to and from an integer with the same number of bits as a pointer. That's what this uint_t get pointer thing is about. I've only provided one direction because the slide is already too big, okay? It also means that we can look at you and figure out how many free bits there are inside of the object. And this is the kind of generic template. It works for pointers, right? We just look at the alignment of the object. We take the log2 of it. I understand that this doesn't compile, right? But you get the idea. We take the alignment of the object, we take the log2, we know how many zeros there are in the low bits, right? We can convert back and forth very trivially. Now we can build a data structure on top of this. So this is one of the most hilarious data structures in LLVM. It's a pointer int pair. And it is the size of a pointer, okay? And so it takes a pointer type, right? It takes the number of integer bits that you would like. It takes an integer type. And it takes this traits object that describes that pointer type. We need to make sure that the integer bits fit into the free bits of the pointer type. But if everything fits, right, we can shift things around, we can mask things in and out, and we get to reuse these low bits. It's pretty nice. Making sense? Everybody like this little clever data structure? There's so much more we can do with this. The next thing we realized is, right, some of the time we have indices instead of pointers. But the indices, they look kind of like pointers, right? They're smaller usually. They don't need all 64 bits. We want a way to store integers like they were pointers, with a bunch of 0 bits at the bottom where we aren't using the data. And so we built this pointer embedded int type, which takes an integer type and the number of bits that integer type needs, and it stores that integer in the high bits of a pointer and leaves the rest of the bit 0. And then we have the pointer, the traits class, where we surface to other users, by the way, we've got free bits in our object. The low bits are all zeros. And we tell them how to convert to and from the object, right? And this allows us to wire in integers as well as pointers into this pointer-integer pair. Making some sense. We can go a lot further, though. Turns out a pointer-integer pair is a pointer-like type. It has zeros that are free in the low bits. We can surface this. It's a fairly simple computation. You take the free bits of the original pointer, you take off the integer bits you're going to use, you have that many free bits left. And so we can build nested pairs like this. And we actually use this to kind of build up data structures, all of which reside within a single pointer's memory, okay? Then we get to my favorite one of these. And there's a lot of code missing here, I'm sorry, but this is what kind of ties it all together. We now have a pointer sum type, okay? So I'll step through. We start off by defining this kind of nonce class template. All this does is bundle a particular n value, a particular pointer-like type, and a traits class for that pointer-like type, okay? Now the n value has to be a particular value to discriminate one pointer type from another pointer type. So you can't have these things overlap. We then build up this pointer sum type class template, okay? And we parameterize it with some number of member types here, but they're actually member templates. They're actually instantiations of this pointer sum type member, okay? And so each one of them associates a particular value with a particular pointer-like type. We also give it a tag type, which has to be some integer-like type, usually an enum. And what we do is we store the tag type value in the low bits of the pointer, and we then use the tag values to make a nice discriminated union between these different things, right? It's variant, but with a lot of time spent packing bits into smaller and smaller sizes, and not a lot of time spent on really fancy APIs or exception safety. Don't need them, they're just pointers, right? They're all very small little objects. And we have nice little helper methods, right? We can get the tag value out of this. We can test whether a pointer sum type is a particular pointer type. If we can do a get, which will try to get a particular pointer type out, and it'll give us a nice null representation if the tag is set to a different value. And so we can write little, pattern matching like libraries on top of this. And we have just gobs of this all over LLVM's codebase. Okay. Everybody following this pointer sum type craziness. Okay. So then we can use this to build one of my favorite all-time hybrid data structures. This is called a tiny pointer vector. And this, too, is a pointer-like type. Okay, so how does this work? What we do is we have an enum, which describes two states for the vector to be in. One of them is an inline state. This actually has small size optimization built in. One of them is an inline state, the other one is a vector state, okay? And tiny pointer vector, right, it has a type, so we know that. And then we build up this sum type here, okay? And the sum type uses this enum to discriminate between either a pointer type, which is t in this case, which is stored inline, or a pointer to a vector, right? A unique pointer to a whole vector we've allocated somewhere on the heap. And then we have just that sum type as the value. And we can write, I've written out just, operator square bracket to kind of give you a feel for what this ends up looking like, right? We go in, we check whether we are in the inline state, right? If we are in the inline state, we don't really need to know what the index is. There's exactly one index available. And we just give you that pointer value, directly. No heap allocations, nothing at all. And if we're not in the inline state, then we forward down to an actual vector allocated on the heap. The rest of the methods look exactly the same as this. So the most useful place for this is when you need a multi-map, all right? Because it turns out we don't like multi-maps. We like those three things I presented earlier. We like vectors, sets, and maps. But it's really annoying to put an enormous small size optimized vector into the value of a small size optimized map. You end up with something that is not very small or fast or optimized. But what we can do is we can, if we happen to have pointer-like value types, we can put this tiny pointer vector into the value of a dense map. And it's only the size of a pointer. And so this remains very compact, very, very small. And in a lot of cases, if you have only one, right, this will actually be just as fast as a pointer. It won't use any extra memory. But it'll gracefully degrade and allocate memory as necessary to handle larger and larger sizes. And this turns out to be incredibly useful in LLVM. There are a lot of cases where you have a multi-map because you have to have a multi-map, but in the overwhelming majority of cases, you have one value or zero values. We can even address that here. And I think this one in particular, I would love to see someone implement this with an allocator. Okay, I think this would be really challenging to get with an allocator. Okay. The last tip, of course, is use bit fields. I don't have to tell you guys about this. This is the classic way you do bit packing. But I couldn't not mention the other fundamental thing we do to reduce the size of our objects in LLVM and Clang. Okay, so we've come up with this elaborate system of making things small. And once we make everything very small, we put them into these three data structures: a vector, a set, and a map. The set and the map are these open addressing hash tables that we probe quadratically. We're often using pointers as our identity. So we have a real problem when we need ordering, okay? Like a real problem. I mean, you shouldn't be relying on the ordering of some kind of hash table anyways. It's a really bad idea. We're trying to make it non-portable with the change to the standard because it's such a bad idea. But if you want to get worse, you really, really don't want to rely on the ordering of a hash table keyed on a pointer. Because if you are on a system with address space layout randomization, you are going to have an extremely bad time. It does not work well at all. And this is actually a common bug we have in LLVM because people make this mistake. So it's important to think about how you get ordering back when you need it. Of course, if you have any possibility to sort a vector, do so. This is fantastic. If you have some fundamental ordering property you can simply assert over your data set, you're home free. You've got a great solution. But you don't always have this. Sometimes you do not have an intrinsic ordering to your data. You have to find some other way of putting your data together, and you still need it to be ordered. This comes up a lot in compilers where we need to be deterministic in our behavior, and we really have to be deterministic in our behavior. We don't even care in many cases which ordering we use, but we have to use unordering. And this is a real challenge when you've built up all of your data structures around unordered containers, okay? And so we need some techniques here. This gave rise to another data structure, of course. This is our set vector. And it does exactly what you would think. It's completely dumb. I've actually copied all of the important code here because all it does is it takes a vector and a set, okay? And when you insert into this thing, it checks the set first and then puts it onto the vector. And when you want to iterate it, it just walks the vector. There is no rocket science here at all. And this thing is incredibly efficient and incredibly fast. We use it all over the place in the compiler, and it works wonderfully, okay? And we can, of course, generalize this to a map, okay? And with the map, we have to be a little bit more careful, right? But we just have a vector and a map. And we even get to do something really nice, because we don't want to store the values twice. We can rely on keys being small. I mean, we really do rely on keys being small, but the value type might be larger. It might not be something we can duplicate everywhere, right? We might not want copies of the value all over the place. But we can solve that with this, because we have a vector. And so we actually just have the map be a map to an index into the vector, right? And so even to build up this data structure, we're literally reusing the concepts from the rest of the talk, okay? And so this is how we kind of piece together the kind of fundamental things we need in order to have this. Now, there's one more cool trick that I wanted to mention here. And LLVM doesn't implement this yet because we haven't gotten to it yet for whatever reason. The cool trick here is to think about what we're doing with a small vector and a small map, or a small vector and a small set. They're the same difference, okay? So when we're doing these things, we're allocating these small buffers, but we're allocating two of them, one for the vector and one for the set. That's a little unfortunate. What's more unfortunate is that it doesn't always make sense to use a, hashed, probed, hash table data structure if you have a very small number of values. If you have a set of like 4 things, that's overkill. It's actually slow. And it would be really nice if instead, when we had really small containers, if we actually just used kind of a linear scan, right? Rather than doing any kind of fancy probing and hashing. And if you think about it, if we do a linear scan and we have this kind of combined set vector or map vector, and we do a linear scan here, we're gonna have 2 different small buffers, both of them with a linear ordering of values, and we're gonna do a linear scan over them. Well, that's wasteful. So we can actually change these data structures to share a single small buffer, okay? And then we can do the linear scan there, and that's the vector when it's small, and then as it grows, we can allocate ourselves a set, and we can allocate ourselves a big vector, and we can fill it up, and we can do the proper hash-based set operations. And so this stuff scales really, really nicely. We haven't gotten to that because this implementation is actually fast enough that no one's complained, right? No one's actually run into this. But there's even more we can do to kind of, tweak and tune this small size optimization to really deliver the last mile of performance. Oh, right. So I just presented 2.5 small size optimized structures and an incredibly crazy amount of code doing kind of pointer bit packing. And I've gotten absolutely no questions. Yes, there's one question.
A question about your tagged pointers. How do they play with CPU prefetch?
A question about the packed pointers, how do they play with, sorry, can you repeat that last part?
CPU prefetch.
How do they play with CPU prefetching? They're not the most friendly things to CPU prefetching, sadly. At the same time, if they're in the cache and we can load them and put them into into registers in the pointer form, the prefetcher will still do it. It's looking at the actual load operation, right? The operand to the load operation is actually the pointer kind of restored. It means that there's less time it can see it ahead of time. But we can also insert explicit prefetching that does that arithmetic to get rid of the integer bits and to produce a pristine pointer for prefetching if you need it. By the way, if you do have questions, please come up to the microphones. And I'm already nervous because Howard is headed up to a microphone. Yes?
With small set vector, how do you remove items? How do you know which element of the vector portion the item's in?
So the question is, with a small set vector, how do you remove items? Slowly. Specifically linearly. We walk the entire thing to find them. It's not great. We've looked at doing a small set vector the exact same way we do the map vector so that we actually have an index. But it is a lot of overhead, and it turns out almost all of the users we have for set vector don't ever remove things until they're finished, and then they delete the whole thing. And so it's somewhat tailored to the use cases we happen to have. Okay, Howard, go ahead.
Hello, my name is Howard Hennett. I noticed that you're completely ignoring the issue of time zones.
How could I have missed that?
Nice talk, thank you very much.
Thanks. By the way, in case anyone's wondering, Howard has a great talk about time zones. Yes, John.
Okay, my name's John Lakos, and I have something to do with allocators, but that's not my question. The first question is, can you tell me when you're ignoring the low order 4 bits, why is it 4 zeros and not 2 or 3?
The question is why, oh my goodness, this was way back. Why was this 4 zeros rather than 2 or 3 zeros? I have many answers for you, unfortunately. Number one answer is because I wrote the code, ran it in GDB, and that's the number I got. The number two answer is because I'm running on a Linux 64-bit system, and this probably reaches out to malloc, and malloc on my Linux 64-bit systems and most people's Linux 64-bit systems just happens to always give you 16-byte aligned memory.
Okay, that works. I couldn't figure it out.
Yeah, no.
I have one more question. It's a very complex space when you talk about the size, locality, and doing bit operations.
Yes.
And obviously, if you have, and the access, if you have sort of arbitrary access in a list versus if you have sequential access. But my question is, I guess, can you give us some insight into where the higher cost, and I think we'd agree that doing bit operations can be a higher cost than not doing the bit operations, having something that's slightly bigger but still small enough to fit inside cache or cache lines, et cetera?
So the question really is, at what point do we start seeing the cost of doing the bit packing outweigh the benefit of compacting our data? This is a great question. So this is fundamentally the cost we're paying, right? This is the thing that does most of the bit packing. So the key insight here are a couple of things. One, while there's a lot of code here, there's not a lot of dynamically executed code, right? So one thing that helps us is that things like the computing the shift values, computing the masks, all that happens at compile time. It's all const expr. So what we're actually paying for in terms of overhead are shifts and masks and ORs. And processors, those are the instructions processors are fastest at in the entire world. So the overhead here is remarkably low. I don't know of any point at which we have measured an overhead of doing bit packing into pointers. I mean, that doesn't mean it doesn't exist. It almost certainly exists, but it's very, very low. The other thing to think about is if you have a 1 or 2 or 3-bit integer and you have a 64-bit pointer, anything you do other than pack those bits in will waste, 8 times the number of bits at least as you had in your integer. And so the savings are relatively large to the problem at hand.
So I've seen in all of your map examples that you store both the keys and the values in a pair. Is there any situation where it's more beneficial to store all the keys together, all the values together, maybe when you have a heavy lookup situation?
So the question is, in all of my map examples, which are further back here, eventually, we store the key and the value in a single bucket, like in a pair in a bucket. This is true. There's a lot of interesting ideas around having separate buckets for keys and values. We don't do that. I think that there probably is a win there, especially for fairly sparse hash tables. But we don't see a lot of win for dense hash tables. The real problem for us is that we're going to have to actually examine the key. If we could cheat and not look at the key, that would be a huge win. If we were walking large portions of the hash table, then it would also be problematic because we'd be skipping over a bunch of value entries. But if we're walking large portions of the hash table, we're probing. And we shouldn't be probing that much. We should be growing the hash table or fixing our hash function. And so I don't think that's really the biggest thing. The biggest wins we've seen, and these aren't in LLVM actually, this is more in Google's code, are around doing a better job of hashing and probing to look at fewer keys, right, rather than trying to separate the data structures. You're already very random access, and so I worry that you're just random access into 2 arrays, and it doesn't help you as much as it does in kind of sequential patterns. A lot of that though stems from the fact that we work very hard to not iterate the actual map. And if we were iterating it, I think that'd be a different question. Yes?
2 questions in this regard. Do you have any relative performance measurements that you can show us to compare these structure access with their counterparts? And the other, you mentioned using bit fields. Are you talking about struct-defined bit fields or bit masks in the traditional C bit mask sense?
So 2 questions. Let me deal with the first one. So the first question is, do I have relative performance numbers? And I'm embarrassed to say that I don't really. Anecdotally, when we have made changes to the compiler to introduce these kinds of data structures, we have seen very, very dramatic performance swings. Usually, though, that's because there was a very bad problem to start with. A lot of what LLVM is doing is systematically following these patterns so that we kind of take off the broad creep of performance at the bottom of our stack. If you write benchmarks, you can measure very dramatic performance differences, though. I always hesitate to do that because the benchmark's actually misleading here, right? Real code doesn't look like a benchmark that does nothing other than like access a small hash table that's in the working set. The second question was about bit fields. When I say bit fields, I mean bit fields as in bit field members of a struct, but they're present in both C and C++. They're not a C++ specific construct. I certainly would not advocate anyone manually pack bits when they don't need to, right? Like the code required to pack the bits in here is horrible, right? You don't want to write this code. You want to actually use a bit field in a struct if you can.
Right. I guess I was referring to the traditional performance difference between using a bit field in a struct versus using bit masks with the math.
So if you see a performance difference in your implementation between using a bit field in a struct and writing out the math manually, you should file a bug with your vendor because there's no reason for that. If anything, the bit field should be substantially faster.
So you mentioned small vector impl, type erasing the size of the small buffer being an advantage. I would expect you can go one step further and use something like GSL span to even generalize across different kinds of containers.
So the observation is that you can use something like GSL span to generalize across different kinds of containers. And in fact, the ArrayRef proposal that predates the span proposal was based on an ArrayRef type in LLVM's codebase and Google's codebase. We use it very heavily. The key thing is that you can't modify the actual structure, though. The really amazing thing about the small vector impl is that you can actually grow the container from that reduced data type. Not just inspect it, not just mutate the values within it.
So you talked about using slab allocator to get a better locality.
Mm-hmm.
Have you tried or measured using structure like a deck and pre-allocating stuff, like say P90 what you need, and using that instead?
So the question is, can we instead pre-allocate what we need rather than using slab allocators? The answer to this is yes, and we do this a fair amount. So we'll often reserve vectors to kind of very carefully chosen sizes and then manipulate them, those kinds of things. But they tend to form pretty subtle pitfalls. Okay, because if you ever get that reservation wrong, you then have a very surprising cliff in your performance, where suddenly you have to go and move a large, pile of data to new locations. The other problem is it can be a correctness bug instead of just a performance bug, because you don't actually have that address stability guarantee from any of those containers. Now we could use something like deck to get this, right? This standard deck, but the standard deck data type is really quite bad. I wouldn't recommend anyone use it for anything. If you look at the implementation constraints, the constraints placed upon its iterators and its invalidation constraints, it's painted into a very unpleasant corner, and it has very few opportunities to be an efficient data structure.
Hey, I have a question about the forward list.
Yes.
So usually whenever people iterate over objects, they tend to use them. And when they use them, the forward list prefetches them if it's carefully designed where the pointer is stored. So why would that be not good compared to, say, a small vector of pointers to objects?
So the question is, why can't the forward list do the prefetching for you by pointing out where the next memory location is? And it certainly can. The problem is that next memory location is still dependent on actually loading the cache line with the list entry in it. And so you have this dependency chain. Every next pointer sits on the next cache line, right? And so you can't look more than one ahead, exactly one. And that's a real limitation on modern processors. Whereas if you have an array of pointers, right, every single one of those pointers is visible immediately. There's no dependency, there's no uncertainty, like the processor knows exactly where they're going.
Follow-up question.
Absolutely.
So you're saying that the modern architecture can actually do these loads in parallel somewhat?
In some cases. It doesn't even matter if it can do the loads in parallel, though. merely having the sequential chaining between cache misses is going to cause stalls to become visible that aren't visible if you can actually decouple the two operations. So even if you can just elide one of the cache line stalls loading the next one and overlap some of the operations, you're going to see wins immediately. And even with prefetching, you don't see this happen with linked lists.
Thank you.
Absolutely. Well, we're running out of time, but I have a little bit more time if there's any more questions.
Hi, and do you use some containers like try, and how they are implemented?
Do I use some containers like?
Try, Trie.
Yes. Do we use containers like try? Interestingly, I think there may be one place in all of the compiler where we use try. It's very, very unusual. They mostly show up in things like symbol tables and other kind of text processing operations, and we have relatively few of those in the compiler. I think that's just my personal bias working on LLVM. The try data structures are fabulous things. I'm just not an expert in them at all.
Before answering one of the questions, you mentioned that if there is a performance difference between bit-masked integers versus bit-filled structures, then you should contact your compiler vendor because there shouldn't be a difference. I was wondering, due to ABI standards, if you return in a bit-masked integer, it can be returned in registers and in register accumulator. And do you know if bit-filled structure can be returned the same way? And would that be a reason for performance difference?
I'm not an ABI expert. I know that the ABI allows us to return some structures in registers, though. I would hope that it allows us to return structures with bit fields in them in registers. I also hope that you don't have a function call return in the hot path here. That will, like, even if it gets the calling convention right, even if it gets it in registers, that's still going to be somewhat unfortunate. But you'd need to ask an ABI expert rather than myself.
Chandler, do you guys reclaim bits on the upper end as well? So like on Linux, you have both, on x86 Linux systems, your pointers are 16-bit aligned, but you also are only using 48 bits of address space, or can you not reclaim them because of address space randomization?
So the question is, do we reclaim the high bits that on some platforms and some pointer sizes are actually known to be the same value, whether they're ones or zeros? We actually leave those alone. We leave them alone for a bunch of reasons. Some of it is because there are not as many bits that we can touch there as we might like because of address space layout randomization, as Bryce mentioned. There are also other reasons to leave them alone. So Intel and other people keep warning us that they want to take those bits back, and we listen. And so we're not kind of baking in an assumption about that. We also do want to run LLVM on 32-bit architectures. And all of the pointer alignment tricks here still work on a 32-bit architecture, but if we started stealing from the high bits, we'd have to turn those optimizations off, which would add a lot of complexity. The final interesting observation is we can grow the alignment of our types however much we need to in order to get the number of bits we want. And we do that. And we do that more on 64-bit architectures where we know we have the address space to do it. And so we can just push the bits we need into the bottom by taking that space in the address space rather than abusing the high bits if we need to. So we can take the remaining two questions fairly quickly, and then I want to let the next presenter get up here.
Way back to the beginning, one of the arguments for using small vector instead of std vector had to do with iterator invalidation, but I didn't catch what that argument was, sorry.
So the question is, what was this iterator invalidation that causes a problem with standard vector having a small size optimization? The iterators are not invalidated on move of the standard vector object itself. And if you are in a small size and you have an iterator, it will be invalidated if you move it from one location to another. Because you're actually going to copy from one inline buffer to the other on move in a small vector.
But not in a, okay, thank you.
So this may be a 10-second question. I may be misinformed, but the piece of information from this that's going to have the most impact on my code is that you said bit sets should be faster or the same as bitwise math on integers that we've all done at some point. So the reason why I use integers directly in my code instead of bit sets is that as someone who's read pieces of the standard but not cover to cover, I see a number of times I'm reading through something and I say it says if t is not a bit set, and then lists a whole bunch of other rules. Are there things I should be worried about there, or am I just being neurotic?
No, they're kind of terrifying. I still think you should use them. I think it's less terrifying than writing complex math yourself and hoping you get it right and then debugging it when you get it wrong, because I hate debugging my code. They're not, the rules aren't going to bite you too badly. They mostly are caught by compiler error messages. These aren't like, oh, your code's going to crash randomly without warning. The rules come in two places. You can't form references to bit fields, to bit field members, which is a little annoying, but you can work around quite easily with something like a reference wrapper. And the second one is you have data race constraints with bit fields. All the bit fields are essentially merged into one large integer for you, and that's what the any access is to. And so it accesses the entire memory location of the merged set of bit fields. These don't really come up in kind of day-to-day stuff. LLVM, we have had far more bugs with people writing math than with the bit fields themselves. So I would generally lean in that direction. All right, well, thank you all very much.